Okay, so today we're looking at a short lecture on probability, and this is geometric probability. And this is one of my favorite types of probability because it makes more sense to me. Instead of binomial probability where you're selecting a certain number of people and then seeing if they do something, this is a type of probability where we're waiting for something to happen, and then once it happens, the problem is done. So it makes a little bit more sense to me personally. So we're looking for the first time we find a success. So we are looking for the first success. Okay, so when we look at geometric probability, we've got a formula, but you might not actually use the formula. So let me write it down, and if you want to use the formula, by all means use the formula, but then as I do the problem, I'll show you what I mean by not using the formula. So here is our formula. It says the probability of the nth, okay, and that is the nth, it's not n, but the nth, is equal to p times q to the n minus 1. So remember that along with every success is going to come failure, but this time what's going to happen is we're going to have just one success because we're looking for the first success. Okay, now the examples that I have for this are a little bit, what's the word? They're not PC maybe, but when I learned geometric probability, these were the examples that I learned with, and I just always remembered them, so they work real well. So let's go ahead and use them anyway. So the first one says that 2% of people will pick up a hitchhiker. Now, remember, hitchhiking is dangerous. You shouldn't hitchhike, you shouldn't pick up hitchhikers. So there's my little spiel about it, but again, we're using the example anyway. Let's say that you are hitchhiking. And you want to find the probability the fifth car you see is the one that stops to pick you up. All right, so you're gonna be out there hitchhiking with your thumb out, and you're not gonna look for how many cars are gonna pick you up. You're going to wait until a car picks you up, then you're gonna get in the car and you're gonna go. So what we wanna know is what's the probability that you're out there hitchhiking, and the fifth car is the one that stops, which means that there are gonna be 4 cars before that that just pass you by. So we can use the formula to do this, or we can use kind of making those slots like we've done before. So if we make 5 slots, these cars are going to pass you. And if they pass you, that means that they are failures. They didn't stop to pick you up, they're failures. So we can say that these are all failures. And then finally, you're going to get a success at the end. The fifth car is going to be the one to pick you up. So you get 4 failures first, and then the success. Now, if there's a 2% chance that a person will pick you up, that means that there's a 98% chance that they won't. So failure is a 0.98. So we're gonna have a bunch of 0.98s here. And then finally, the last slot is going to be the success, and that gives us our 0.02%. So if we want the probability of the fifth car that we see stops to pick you up, we're gonna do 0.98 to the fourth times 0.02. And if we stick that in our calculator, we get 0.018. So there's a 1.8% chance that the fifth car you see will be the one that stops to pick you up. Now, here we have our problem the way we did it, and here we have the formula. Now, the reason why I'm not fond of the formula and I like to do it better this way is because the way that we have it written down is the way it actually happens. You get your failures first, and then you get your success at the end. But the way the formula has it written is the success comes first and then the failures. So the formula is the same thing that we did, it's just flippity-flopped. And if that doesn't matter to you, then fine, by all means, just plug numbers into the formula. But if understanding how the process works is important to you, then it doesn't take that long to write this out and make sure that you've got exactly what you want. Right? So there is one example. Now, the other example says 16% of people carry a lighter or matches. You need to light a cigarette. Remember, don't smoke, it's bad for your health. Okay, fine. We're using the example anyway. So you need to light a cigarette. Find the probability. The fourth person you meet is the first to have a light. So again, in this example, we've got a situation where you're trying to light a cigarette. So you're gonna go around and you're gonna ask people, hey, do you have a light? Hey, do you have a light? And people might say no to you. They're gonna say no, no, no. But then finally someone is gonna say yes. And once someone says yes, you light your cigarette, the problem's done, it comes to an end. You don't continue to walk around and see who else has a light. You finish the problem and you move on. So we're looking for that first success and then we're done. Now this time, we're looking for the probability that it's the fourth person that you meet that has the light. So if we're going to put 4 slots here, okay, 4 slots, here's the success at the end, but it means that we're going to have 3 failures beforehand. You're gonna ask 3 people and they're all gonna say no. So failure, 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 and then we finally get a success, okay? So that means that when we look at the numbers, if 16% of the time they say yes, then we need the complement, which is 84. So these guys are gonna be 84. So there's an 84% chance of saying no. Then we'll have our 0.16. So again, if we want the probability of the fourth, that's gonna be 0.84 to the third times 0.16. And we'll stick that in our calculator and we get 0.095. So geometric probability is just a short little section to look at. There are problems on Canvas under the files for you to practice, but there really aren't any problems out of the book for this one. So just a couple problems to practice on Canvas. But anyway, so just a short little type of probability, but one that kind of makes more sense to me than binomial probability. Okie dokie, that's it for this one.